Welcome, this is the module 6, that is the week 7 and lecture number 28, and we have just started the steel making, and I have talked about brief history about the steel making, and then I also talked about the slag structure and important properties of the slag like oxidation property, viscosity and basicity. Now, in this lecture we will talk about some very important reaction that is relevant for the steel making and their reaction equilibria. Now, in this lecture the concept that will be covered, first I want to introduce a concept 100% standard state, because when you consider the reaction equilibrium and in the liquid steel, you know, the impurities percentage hardly exceeds 100%. So, most of the impurities are within 100%. So, very dilute solution, and if we want to express the activity of the impurities with respect to pure solid at the standard state, then activity value become very less, of the order of 10 to the minus 3 minus 4. So, it become very inconvenient. So, usually a activity for impurities in liquid iron is expressed in terms of 100% standard state. I will discuss about that, and then I will talk about this oxidation of iron, oxidation of carbon, oxidation of silicon and manganese, right. So, 100% standard states of impurities in liquid iron, as I said, the percentage of impurities in liquid iron hardly cross 100%. Most of them are much less than 100%, and silicon can be little bit high, 1 to 1, that is fine. Now, with reference to pure solid at the standard state, the activity of impurity will be very low values. Just now I said that is the usually, that is the, you know, the Raoult's law, that is here you know the pure solid at the standard state. We consider that is the pure solid at the standard state, because activity do not have any, as you know, it does not have any absolute value. Activity always expressed in terms of some relative value with reference to some reference, right. So, here the reference is pure solid as the standard state, that is, if the solid is pure or the liquid is pure, we assign an activity is equal to 1, right. That is activity, and activity is for the Raoult's law, that is the thing, and the Raoult's law is what? Raoult's law is basically says for the ideal system, when you do not have any interaction between the impurity and the solvent, solute and solvent, there is no interaction, then Raoult's law is valid, and under that condition you can say activity is equal to the mole fraction, right. So, that is the Raoult's law, this is the Raoult's law straight line, this the activity is equal to mole fraction, okay. So, pure solid, so when xi is equal to 1, then activity is equal to 1, that is the pure solid at the standard state, right. Now, in actual system, in non-ideal system, your activity not equal to xi always case, and activity is equal to gamma I into xi, because you have interaction between the solvent and the reactant, solute and solvent, there is an interaction, that is why another term comes into picture, that is called the activity coefficient, right. As a result, you have the activity composition relation like this is the activity composition relation, right. And finally, when it is pure, then activity become 1, no problem. But in some other case, when there is a positive deviation, you have this activity composition relationship is like this. So, this is the, with respect to, this is called the Raoultian scale. Activity is basically represent here in terms of A, this is called the activity with the mole fraction. This is usually the mole fraction xi and the activity of I. So, if you can write it I, and this is the xi versus activity. So, this is the relationship. Now, you can see at infinite dilute solution, in case of the dilute solution also another straight line you can find, that is a Henry's law is valid. In this case, you can find that is this line is called the Henry's law line, basically a straight line relationship between the activity and mole fraction. That means, in the very dilute solution, activity again proportional to the mole fraction. In this case, you can find that the gamma is changing, gamma is continuously changing with composition. But here in this range, you can say gamma is constant in infinite dilute solution, gamma is constant, and it is called the Henry's law, and it is called the Henry's law activity coefficient, right. So, then it is the thing in this, in case of the dilute solution, you can write gamma is equal to gamma E naught into xi, right. This is the activity coefficient, right. So, since it is there, it is advantageous. Now, for dilute solution, I can define another standard state, because the state line relationships is there. There is the activity is directly proportional to, here you can find activity is directly proportional to the xi in this range. So, I can define another state line, another, what is that called? There is another standard state. So, Henry's law is followed, as I said, and therefore, a convenient standard state may be defined in dilute solution, right. How you can do that? You can find that is this thing, that is, you can see from here, if I just enlarge this portion, and then I can get this, okay. So, then this Raoult's law line goes like this, and this is the Henry's law line, and then if you consider that this is a straight line like this, it goes, this is the Henry's law line. So, this is the Henry's law line, it goes like this, and then if I consider that is the Henry's law is valid up to this point, up to 1/8%, right, up to 1/8% Henry's law is valid, and I can define a scale where 1/8% standard state I can define, where I can say that activity is equal to, that is this 1/8% standard state, we can say activity in the other scale, that is the Henryan scale, is equal to the weight percent, okay. So, we have defined another standard state when we say that is the activity is equal to 1 when weight percent is equal to 1. So, if the Henry's law is valid up to this point, up to 1/8%, then you can define in another, and another, it is that called. So, you can define another activity Hi is equal to, you can say this is weight percent of I, right, that I said. So, this is called the activity coefficient on Henryan scale. So, this is another scale, this is not the Raoultian scale, pure solid at the standard state, that scale is not, this is another scale, it is called the Henryan scale. In that scale, I can say that is the activity is equal to weight percent. If Henry's law is valid up to this point, if Henry's law is valid up to 1/8%, that is, it is a straight line portion, then I can say that is the Hi is equal to Wi. And if it is not valid, that it can be found out like this. So, this you understand, that is the Hi is equal to Wi, just another standard state we have defined, where activity in the Henryan scale become 1 when weight percent is 1, because up to this point, because you have the Henry's law is valid. If it is not valid also, then we can, if it is not valid like this, here there is a deviation, in that case I can define that is your, that is the Hi Fi into Wi, where Fi is the activity coefficient, okay, Fi is the activity coefficient in the Henryan scale. There is the activity coefficient in the Henryan scale, and is the interaction coefficient. And then log, there is the log of Fi, you have this thermodynamic, these correlations are there, and where E represent the interaction coefficient of J on I, and W is the weight percent of J, and for J is equal to 1. So, multi-component system, you can calculate what is the interaction coefficient, okay. So, activity coefficient on the Henryan scale you can define like this. And there is a correlation between this activity and this activity also, that is the Hi, that is the activity on the Henryan scale, you can simply correlate with the activity on the Raoultian scale, that is the pure solid at the standard state. And you have also a standard free energy change from the pure solid at the standard state to the 1/8% standard state, if you know, this will be the free energy change. So, thing is that what I said basically in short is that activity of the impurities, it is very difficult to represent the activity of impurities on the Raoultian activity in terms of with respect to the pure solid at the standard state. If you represent that, then the value will be very less, maybe of the order of 10 to minus 4, 5 like that. So, it will be very so for that, for a convenience scale, that is why we defined a convenience scale for at infinite dilution, and it was possible because Henry's law is there, where basically the activity coefficient remain constant. At dilute solution, activity remain constant over a certain range, and So we can define another scale where I say there is the activity is equal to 1 when weight percent is equal to 1, and if the Henry's law is valid up to 1 weight percent, then this is thing, and if Henry's law, if the activity actually deviate from the Henry's law up to 1 weight percent, then we can represent HI is equal to Fi into Wi. That is the thing, we can do that. Okay. So now, so this is, that's why the impurity is basically represented with respect to a different scale, that is called the Henry scale. Okay, and then you can just make a corresponding change into the free energy change. Okay, standard free energy change for this scale change, you have also delta G naught value. So you can always make the delta G naught value for a reaction if you just change the activity scale. If you just change the activity scale from pure solid at the standard state from to the 100% standard state, you have to make only change in the standard free energy change. This value you have to add there. So with that you can do that. Now let us consider the oxidation of iron. Now you can consider the oxidation of iron. You can simply consider this reaction, Fe, FeO, Fe reaction. You can consider Fe plus dissolved oxygen forming the FeO, and now you can see the equilibrium constant is represented, you know, as the ratio of activities of the product to that of the reactant. Now you can see that on the activity of FeO I have represented with reference to Raoultian scale, that means with pure solid at the standard state, where, and also the activity of iron also we have considered, that is the with the pure solid at the standard state, because iron is 95% weight percent in the liquid iron, iron is 95%, so which is very pure form. So I can write like this, but we have represented the activity of dissolved oxygen with respect to Henryan scale. That is the AHO, that is the activity of dissolved oxygen in the Henryan scale we have written here because of convenience. Then the activity value will be between 0, 1 or of the order of 1. It is very convenient. Okay. So only for that, if I just change the activity scale, if I change the standard state to represent the activity, then I have to make a sudden change in the delta G naught, as well as there will be a change in the equilibrium value, right? This equilibrium constant value also there will be change. So this value what you can find here, that is the log of Kfe, this value, and if I represent the activity of dissolved oxygen with respect to Raoultian standard state, then this expression could have been different, little different. Okay, and this expression, now what we can see, it is basically considering that the dissolved oxygen is being represented on the Henryan scale. So it's not a problem. So if you have the proper Kfe value, you can do that. So now let's see, now from this equation what you can do, we can calculate the equilibrium constant at a particular temperature, and then I can calculate the HO. HO means that is the activity of dissolved oxygen on Henryan scale, and HO become WO if the Henry's law is valid up to 100%, right? HO become WO. So you can directly calculate what is the value of WO, because activity of FeO you may consider 1 if you consider Fe is equal to 1, or activity of Fe you can take it 1 because it is the major bulk into the liquid iron. So you can consider activity of Fe is equal to 1, activity of FeO taking at 1, and Kfe you can calculate. So simply you can calculate the dissolved oxygen into the bath from this equilibrium. So for pure FeO, the equilibrium oxygen content in liquid iron you can calculate at different temperature, 1550, 1600 and 1650 using this formula, and you will get the value of 1850, 2330, 2900 ppm like this. Okay. And typically the activity of FeO in steelmaking slag is 0.5. So if you take activity of FeO 0.5, then this value will be just half. So at 1600 degrees centigrade, it will be 1165, right? So of the value. Now this is the oxygen that you can theoretically calculate. Now actually the oxygen content in the turned down sample is around 800 to 1000 ppm. Turned down sample it is around 8000 to 1000, which is lower than the saturation value at the steelmaking temperature, because we know we have calculated the saturation value theoretically and we find its value is 1165, but the turned down sample in the tap steel, it is around 800 to 100 ppm. So it is always less than the saturation value. What is happening? Thing is that because this equilibrium is at the slag metal interface, right? So dissolved oxygen, what you are finding, that is at the interface. Now this dissolved oxygen has to diffuse or has to be transported and to be mixed up with the rest of the liquid. Okay, then only you can get a higher value. But problem is that your mass transfer is rate controlling. There is the mass transfer. You cannot mix up the interface dissolved oxygen immediately. As the FeO is decomposing, there is the FeO is giving this dissolved oxygen, there is the equilibrium oxygen at the slag metal interface. That oxygen not being able to come to the interior of the bath or mixed up with the bath immediately because of mass transfer limitation. That's why that is your turned down sample oxygen concentration appears to be less. So what happens? There is a build-up of oxygen, dissolved oxygen at the slag metal interface, and that oxygen will not remain like that. What it will do? It will basically oxidize the iron oxide to the Fe2O3, higher oxide, because over-oxidation. So it shows the slag is over-oxidized. How? This is the reaction you can consider. This is the reaction that will take place, FeO plus oxygen forming Fe2O3. Okay, so this reaction will take place, and there is an evidence also. That is, if you see the steel making slag, you can find that is Fe3 to Fe2 ratio. That is the ferric to ferrous ratio of the order of 0.3 to 0.5. That means it is not in the form of ferrous form, that is FeO. It is in the form of Fe2O3 also. And that means this reaction goes on there. Because this reaction goes on because you have a lot of dissolved oxygen near the interface, and that is not being able to transport to the rest of the liquid metal. As a result, they are oxidizing the FeO to Fe2O3. So the slag remain over oxidized and always oxidizing to metal. And one thing is that, and if you want to calculate, now since Fe2O3 is there, Fe2O3 has a much more higher partial pressure, that is the decomposition, or you can say oxidation potential compared to that of the FeO also. In Neelingham diagram, Fe2O3 is much above than that of FeO. So this equilibrium you can calculate, then this partial pressure of oxygen will be little higher maybe. Okay. So this reaction may be considered, that is the partial pressure of oxygen for this reaction may be responsible for the chemical potential of the slag, not for Fe-FeO equilibrium. Okay, because this reaction is also taking place, and then Fe2O3 is a much higher oxidation potential. So this partial pressure of oxygen will be greater, and this can be considered. But basically by this reaction, your oxidation potential of the slag can be measured also. So this may be the appropriate reaction. Okay. Silicon reaction is like this. There is the silicon reacting with the dissolved oxygen forming the silica, and this equilibrium constant can be write in terms of the activity relationship like this. And here we can find that activity of silica divided by weight percent. Directly we are writing the weight percent of silicon and weight percent of oxygen square. That means here we are assuming that is the Henry's law is valid. First of all, this activity of silicon has been expressed in terms of Henryan activity scale. As well, we consider that is the activity coefficient is equal to 1. That means Henry's law is valid. Okay. So if under considering the Henry's law as values, that is the activity of the impurities in Henryan scale can be written in terms of the weight percent of impurities. So that is what we have done. So activity of silica divided by this thing, and then silicon, there is a equilibrium coefficient of silicon in terms of temperature can be given by this correlation, and then we can simply calculate taking activity of, that is the, for lime saturated slag, it has been found activity of SiO2 is very less, because activity of SiO2 less because it combined with the calcium forming a very strong compound like dicalcium silicate, tricalcium silicate, those are very strong. As a result, free concentration of SiO2 or the activity of SiO2 decreases significantly. So for lime saturated slag, activity of, if I take this thing, activity this thing, and then simply we can calculate the silicon concentration considering the turned down oxygen ppm into the bath. Okay. So for 800 ppm of oxygen in the turned down sample, if you consider weight percent of silicon in the metal, that is the percentage of silicon in the metal is less than 1 ppm. So thermodynamically, so for lime saturated slag, percentage of silicon into the metal can be reduced below 1 ppm. It is easily possible to bring it down to below 1 ppm, but it is quite difficult to bring it down below 50 ppm, 30 to 50 ppm because of kinetic limitation. So, that is there. In practice, silicon in the turn down sample is around 30 to 50 ppm. It is due to kinetic limitation, because when the silicon is decreasing, then transport of silicon from the bath to the interface, because all these reaction take place some heterogeneous interface like slag metal interface. So, silicon has to transport from the bulk to the slag metal interface, then only it can react. And when the silicon percentage decreases, then the transport of silicon become much more difficult, because become very as a result, because of this mass transfer limitation. So, you cannot bring it down to more than 30 to 50 ppm. Okay. So, that is the one thing. Otherwise, silicon oxidation is very simple in steel making, that we can find. Now, come to the oxidation of carbon. Oxidation of carbon, again you can write this thing, that is the dissolved carbon and dissolved oxygen reacting and forming a, this second bracket means there is the gaseous product. Whatever the CO we are forming is the gaseous. This is the very unique product, unique oxidation product of impurities, because in this sense, because only carbon when get oxidized produces a gaseous product, otherwise all the impurities like silicon, manganese, phosphorus all produce a solid product, and they have to be accommodated into the slag. But this carbon oxidation, it forms a gas and it goes away from the slag, goes away to the atmosphere as a gas. So, as a result, you do not have to retain this oxidation product. In other cases, you have to keep this oxidation product into the slag. So, slag volume increases. So, carbon oxidation does not give any slag volume increase or nothing like that. Anyway, it has another advantage also. This is the only reaction which can be influenced significantly by the pressure, because the right hand side is a gas. So, and the equilibrium constant can be given like this. Again, the denominator impurity concentration, there is the impurity activity is defined in terms of Hendian scale, and Fc, F0 are the activity coefficient of carbon and oxygen respectively in Hendian scale, and W0, Wc are the weight percent of oxygen and carbon respectively. Pcu is the partial pressure of CO. Now, again you can write simply in this way, and if you take Fc and F0 for the time being as 1, you can calculate, then Pc, Kc are correlated, and Kc you can calculate from there as at a particular temperature at 1600 degrees centigrade, you know the Kc value. If F0, Fc you take 1, then simply you can calculate, and partial pressure depending on the what is the partial pressure of CO, your value of Wc, that is the dissolved carbon into the bath, can vary. And turn down WO, you can take the turn down sample around 800 ppm, and based on that you can calculate the value of carbon concentration into the bath. Okay. And these are basically at different temperature, as I said, at different pressure you have different correlation. The solubility product Wc into W0 is basically a constant at a particular pressure and temperature. At particular pressure Pcu is constant, at particular temperature Kc is constant, and activity coefficient for a particular composition is also constant. So, solubility product left hand side is a constant. So, oxygen percentage and carbon percentage. So, you can see at different pressure, this is the solubility product line like this. So, obviously, as the pressure decreases, so you can keep a very low activity of oxygen and carbon is possible to maintain into the bath. So, this is the line at 1 atmospheric pressure, this is the line that is being followed, and 1 atmospheric pressure, and at 1600 B line you can consider for 1600. So, this thing. So, most interestingly at 1600 degrees centigrade, and if we assume Fc is equal to 1, F0 is equal to 1, and percentage of oxygen in the turn down sample to be 800 ppm, then the equilibrium carbon in the metal is estimated at 200 ppm. Okay. So, 200 ppm you can lower down the dissolved carbon, that is the carbon by oxidation, you can lower down the carbon level in the bath to the 200 ppm. Below that it is not possible even at 1 atmospheric pressure at a particular temperature. At 1600 degrees centigrade, 1 atmospheric pressure, you can lower the carbon to the 250 ppm only. Below that it is not thermodynamically possible. And since and one thing, since the LD kinetics is very fast, then bringing down the carbon to the equilibrium level is possible. What I wanted to mean, you can attain this 250 ppm in LD also, because in LD kinetics is very fast. because of emulsion formation, and you can assume that it will come to an equilibrium. So, then 250 ppm you can achieve, that is possible, but below 250 ppm, if you want to make 50 ppm, 100 ppm carbon steel, it is not possible at all in the LD, which runs at 1 atmospheric condition. Okay. So, that I have said, but it is not possible to bring down the carbon in steel below 250 ppm by LD process that take place at 1 atmospheric pressure. So, if you want to make a very ultra low carbon steel like for stainless steel or something else, IF steel, so in that case you have to take the help of vacuum, because this reaction will respond to the vacuum very significantly, because the product is a gas. So, under vacuum we can easily lower down the carbon percentage to a very low value. So, you can see on the order of 10 to the minus 2 weight percent is not a very difficult thing, that is of the order of 20 ppm, 30 ppm, of the order of 2, that is 30 ppm, still you can easily do that under vacuum. But under only steel making condition, that is not possible. That is the very important message is there. Now, I will come to the next, that is the manganese oxidation. And manganese oxidation, manganese is also a very unique impurity in sense, that is the manganese when get oxidized from manganese oxide, and manganese oxide is a basic oxide, unlike silicon and the phosphorus, they basically form a acidic oxide, and they can be easily retained into the slag by using the basic, that is by using lime. Because lime is a basic oxide, strong basic oxide, and they can easily form compounds with the silica as well as P2O5, and they can be retained into the slag without their reversion into the liquid metal. But basic oxide, MNO cannot form a very strong compound with the lime, because lime is also a basic oxide, calcium oxide is a basic oxide, MNO is a basic oxide. Their activity coefficient basically not less than 1, it will be greater than 1, because they will repel each other. That is the problem, that is the MNO cannot be very easily kept into a basic slag. If the slag is acidic, then MNO can be kept in, because it is a basic oxide. In acidic slag it can form compound and it can be retained into the slag. But if it is basic slag, when you form a basic slag, then retaining MNO is very difficult. Okay. So, that is from physically, this is the uniqueness of that is the unique impurity in the liquid iron, okay, that forms on oxidation a basic oxide. All other oxide are acidic oxide. So, and then that is you can write the Kmn, that is your equilibrium constant, you can write in this activity correlation like this, and then you can write Kmn prime, that is called the equilibrium quotient. Then when I write in terms of the percentage, weight percentage MNO by percentage of FeO by percentage of Mn, right. So, considering the activity coefficient equal to 1, okay, and also the mole fraction converted to the percentage of MNO here, and mole fraction of FeO converted to the percentage of MNO here. So, these are only a constant relation. With the help of a constant you can take care of. So basically Km is converted to Kmn prime, that is called the equilibrium quotient, Kmn prime, okay, and you can write this activity relation in terms of the concentration relationship, okay. And then this is equal to, you can simply write again the Kmn into, and here if you can take that you can correlate with the equilibrium constant and the activity coefficient relationship, because the activity of FeO you can write mole fraction of FeO into gamma FeO, and activity of MNO also mole fraction of FeO into gamma FeO, like that. So, from there you can come to this thing, you can simply write this relationship, it is nothing, that is what I am telling, that is you can simply write MNO XMNO into gamma of MNO, like this. So, that way it is coming, and similarly your activity of FeO also mole fraction of FeO and the gamma FeO, that way you can write, and then you can write this Kmn of this thing is this side. Okay. So, then you can write this is the partition coefficient, you can write in terms of weight percent of MnO in the slag divided by the weight percent of Mn into the metal, and to be very precise it should be dMn should be represented as, that is the percentage of Mn in the slag divided by percentage of Mn in the metal. That can be, you can write it as some constant time percentage of MnO by percentage of Mn. Okay. So, this is the way dMn you can write in terms of the percentage of MnO in the slag divided by percentage of Mn in the metal, or percentage of Mn in the slag by this thing. This is a constant, only factor of constant. Okay. So, that is called the partition coefficient, and then partition coefficient you can simply correlate with the percentage of FeO into Kmn and gamma FeO by gamma MnO. Okay. So, that is the thing. So, now you can find that partition coefficient depends on this gamma FeO by gamma MnO ratio. Now, you can see both are basic oxide, FeO and the MnO both are the basic oxide. So, with increase in basicity it is expected that gamma FeO will increase and the gamma MnO both are supposed to get increased, okay, with increase in the basicity, gamma MnO by gamma FeO. But here you can find there is the ratio, that is the gamma FeO by gamma MnO, this ratio basically decreases and then it becomes constant at a particular value, beyond that thing it does not change. So, it decreases because MnO become higher than that of the FeO. So, response of MnO with the basic oxide is more, that is the gamma MnO increases more compared to the gamma FeO, increase in the gamma FeO, that is the basic nature of MnO is more than that of the FeO, that it shows. So, as a result what happens? So, it decreases, the ratio decreases. So, that is the rate of change of increase in gamma MnO is greater than that of FeO. So, denominator become more with increase in basicity, so it decreases. So, and then after that time, after certain basicity this thing. So, fine, you can get that. So, at high basicity what happens is that this value become very low, as a result dMn become low. So, if you decrease this value, this become low. So, partition coefficient become low. Partition coefficient low means that is the percentage of MnO in the slag become less and Mn into the metal become high. Okay. So, that is the way. So, what happens then? Basic slag dMn decrease, it means that some of the MnO into the slag that will revert back to the metal phase. That is the percentage MnO decreasing means with increase in basicity means that is the sum of the MnO is reverting back to the metal. So, as a result that is the percentage Mn also mean in the metal increases and percentage of MnO in the slag decreases. So, this decreases. So, what I want to mean is that basically if you decrease this value, basically what you are doing, you are decreasing this value and you are increasing this value. So, this is what is happening. So, under basic slag condition, so what you get, when the partition coefficient becomes minimum in the basic slag condition, right, that is true. And it invokes, that is the manganese reversion in the steel melt, that is here. So, some manganese reversion take place. So, basic slag condition manganese reversion take place, that is the sum of the manganese oxide into the slag breaks to manganese and the manganese goes into the, because manganese, because MnO do not become comfortable in the basic slag, their activity increases. So, obviously, since their activity increases, this reaction, if the activity increases, this reaction move in the backward direction. Simple thing is that as you increase the basicity, your MnO activity of MnO increases and then reaction moves in the backward direction. So, that basically happens. So, it is simple. And you can see here we have plotted the what is called, that is the partition, that is the manganese capacity of the slag. Manganese capacity of the slag is defined as, you can see, percentage MnO by percentage Mn, that means the partition coefficient, and it is normalized with respect to the percentage of FeO, because obviously if FeO is higher, the manganese will be oxidized more. Okay. So, at a particular oxidation, then you cannot consider, you cannot calculate the capacity of the slag. Capacity of the slag you have to normalize with respect to the percentage of FeO. That is for a, so in this case this value basically will be independent of percentage of FeO in the slag. That is the oxidation property of the slag, right. So oxidation state of the slag. So then it will only represent the capacity of the slag, how much manganese the slag can hold at a particular oxidation potential of the slag is called the holding capacity of manganese, or that is called the manganese capacity of the slag. So it is defined as partition coefficient with respect to the, right, normalized with respect to the oxidation power of the slag. That means at a particular oxidation power of the slag, so how much manganese a slag can hold, that can be represented by this term. Okay, so this value you can find, and this is the basicity, and basicity is not the common basicity you can find, a percentage of CO plus 1.4 percentage of MgO, because after CO is the most influential basic oxide into the slag, and then MgO is there, because other oxides are not that effective in capturing the manganese into the slag, and divided by the SiO2 plus 0.84 of P2O5. So this is the way the basicity has been defined, and you can find that in the acidic open hearth furnace, that is acid open hearth furnace, manganese capacity is maximum because the slag is acidic, and when the slag become basic like BOA, there is a basic open hearth, in all these cases the activity become very low. So you can find capacity of the slag for manganese, capacity of the slag become low. Okay, so under basic slag condition the manganese capacity is quite low, and acid slag condition the manganese capacity is high. It is obvious. So manganese capacity become minimum for the basic slag. So you can this is the two book, E.T. Turkduggan, Fundamentals of Steelmaking, very good books, and from here we have taken some figures, and Ghosh Chatterjee. And conclusion, first conclusion is that the turned down oxygen in the tapped steel from LD is found to be much lower, is not much lower, is lower than that of the saturation value. We have seen there is a turned down sample, the oxygen percentage is around 800 to 1000 ppm, and at the 1600 degrees centigrade calculated value from thermodynamics, it is around 1165. So it is less than the saturation value, and it indicates basically over oxidation of the slag. Okay, the slag is over oxidized because the oxygen from the interface not being able to penetrate into the bath as fast as it is producing at the interface. As a result, the oxygen, there is the accumulated oxygen oxidize the FeO to Fe2O3, and the slag get over oxidized. As a result, slag remain always oxidizing to the metal. And it is difficult to lower the carbon content in liquid steel below 250 ppm by the LD steel making, which take place under 1 atmospheric condition. So if we want to make very low carbon steel, we have to go for the vacuum, and under vacuum C-CO reaction, there is the carbon oxidation response very significantly because the product oxide is gas, and silicon can safely be reduced to 50 ppm under basic steel making condition. And manganese reversion is likely to take place under basic slag because manganese oxide is a basic oxide. So under basic slag condition, activity of MnO in the slag increases. As a result, activity of MnO increases. As a result, the reaction in the reverse direction proceeds and forming manganese. Okay. So this is about this some basic oxidation reaction like iron oxidation, carbon oxidation, silicon oxidation, and the manganese oxidation. In the next lecture, I will talk about the dephosphorylation. Thank you.